Hello, this is Bradley Van Dam, and I'll be doing exam chapter 24, and I'll be doing questions 21.4.1 through .4. So let's get started. So for question A, we're given the information: the plates of a parallel plate capacitor in a vacuum are 2.7 millimeters apart. That is D. 2.7 millimeters apart and 2.25 square meters in area. When you apply a certain potential difference across a capacitor, the surface charge density on the positive plate is 1.4 times 10 to the negative 5 coulombs per meter squared, and asks us to calculate the capacitance of the capacitor. So we are given, and then also the positive 1 point. Meters squared. That's our charge density, surface charge density. So we're asked to solve the capacitance of the capacitor. So we can utilize this equation right here. Capacitance equals constant times area over part, looking for C. And that's a constant 8.85 times 10 to the negative 12th times 2.25 over that distance apart, actually that's in millimeters, so let's just say, how do you put that, 0.0027, and then if we put that in a calculator, .0027, and then we get 7.38 times 10 to the negative 9th. It's in farad, so 7.38 farads, and that's part A. And part B asks us to find the potential difference in this problem. So to do so, the end equation I want to use is electric potential equals the electric field times that distance. So I want to solve for V, but I do not have my electric field yet, so I'll just do a little side note. Electric field equals, and then the surface charge density over the electrostatic constant, looking for E on this side. So we're given that surface charge density 1.4 times 10 to the negative 5th, and then divided by the constant again, so 8.85 times 10 to the negative 12th. Let's do that out. I was going to try to do some -5 over 8.85 times 12. We get this massive number, which is essentially 1.58 times 10 to the 6th, so 1.10 to the 6th, and that is going to be in volts per meter as for the units of electric field, and then we're just going to plug that back into this equation to find the electric potential. So V is going to equal the electric field we just found multiplied by the distance apart, 1.58 times 10 to the 6th, and that distance again is just 0.0027 meters. So I'll just multiply. Actually, I'll just use it as if I'm rounding. 1.586 times 0.0027, and then we get 4,266 volts. That's for part B. Okay, so that is the two parts for question 4.1. .4.2. So this one is for parts C, D, and E. So this problem, it says one model of a parallel plate capacitor in a vacuum is advertised as having a capacitance of 8.87 or 8.7 nanofarads. When you disassemble one such capacitor, you find that the plates are the area of 4.5 square meters, and it says what is the space between the capacitor plate, or the capacitor's plates. So we're looking for that D distance. So we can use the same equation we used up here for capacitance, but now we're solving for D instead. So we can say C equals E naught times A over D, looking for D. Just rewrite that, and that's essentially, what do we do? Yeah, we just multiply the D over, divide the C over, and then it's going to be D equals, and I'll just start plugging in stuff from here. So then we have, because everything will be, the D will be left alone, so the constant 8.85 times 10 to the negative 12th times the area, 4.5 meters square, or square meters, and then we have, this is, the capacitance, yeah, so we're dividing by, so nano, so that's times 10 to the negative 9th, so 8.7 times 10 negative 9th. So let's do that. Actually, you know what? I'll use what I have. Save myself some time. 4.5. And then we get 4, so that's 1, 2, 3, 4.5, I'll say 58 times 10 to the negative third, and this is distance, so this is going to be in meters, and that's part C. So part D asks for, or so it says, when the potential difference between the plates is 5.5 kilovolts, what is the charge on the capacitor? So now we're looking for Q for part D. So the equation we can use is the charge Q equals capacitance times potential, and we're looking for Q, so we can leave this equation as it is. And we're giving capacitance, so 8.7 times 10 to the negative 9th times, let's see. I'm thinking, so V here. Okay, yeah, so in the problem it gave us 5.5 kilovolts. Okay. So V is already accounted for, 10 to the third. And then we get our charge equal to 4.78. Let's do 79. I want to make sure I got that. 4. 5, yes, 4.79, 10 to the negative fifth. And that's charged, so that's going to be in coulombs, part D. Okay, so last part for this second question, part E, says when the potential difference between the plates is 5.5 kilovolts, what is the magnitude of the electric field between the plates? Okay, so we can essentially just reorganize this equation we used for the first question. So instead of V equals ED, we can solve for the electric field and say E is what we're solving for equals electric potential over the distance apart. And we know the potential and let's see, the distance. We solved that. Yeah, we solved that in part C. So we're just combining all three of those parts together. So we're going to get equals 5.5 times 10 to the third divided by that 4.58 times 10 to the, what was that, negative third. That's going to equal, let's find that out. Third. That is 1, 2, 3, 4, 5, 6. Or we could just say, since it's 6, we could just say, we could say kilo, give it a kilo prefix. Yeah, let's do that. So let's say, instead of doing like 1.2 times 10 to the 6, let's just say 1200, but let's say kilovolts. Yes, that should be right. So the answer will be for the electric field, 1200 kilovolts per meter, and that is for E. All right. Okay. Oop. I was thinking in my head, third question, and I wrote down 3. 24.4.3. Okay. So this one is going to be parts F through I. This problem gives us information. It says a spherical capacitor has vacuum between its conducting shells and a capacitance of C equals 125, I think it's in micro, oh no, that's picofarads. The outer shell has an inner radius, so to say, R in 9 centimeters, so I'll just say, yep, meters. And it says, what is the outer radius of the inner shell? Okay, so think about this for a sec. Okay, yeah, so we can use this equation for capacitance to find the outer radius of the inner shell. We can use C capacitance equals 4 pi, that constant again, electrostatic constant, times, and A and B are the distances, or the radii, if you will, minus A. And so in this case, we're going to treat A as our, how do we want to do this? Let's treat A as that's what we're solving for. So we'll treat that as the I'll just say, the R out is going to equal our A, the outer radius of the inner shell. So let's plug in, actually let's not plug in some values yet. Let's get this guy, trying to think the best way to do this. Okay, yeah, so let's divide 4 pi E naught. So we get C over 4 pi E naught is equal to AB divided by B minus A. And then let's see. So, okay, then we can start plugging in values. So we have C, that is 125. I'll convert that just to SI times 10, super tiny number, 12 times 10 to the negative 12, divided by 4 pi, electrostatic constant 8.85 times 10 to the negative 12, uber tiny number, equals, again, AB minus B minus A. So let's simplify this. Let's actually just do that out here. So 125 times 10 to the negative 12th divided by 4 pi 8.85 times 10 to the negative 12th. And then just round that off to 3. Let's do 1.12 equals AB divided by B minus A. And so now it's just a matter of just algebra at this point. So we can we can multiply B minus A over here to the 1.12. So we get 1.12B minus 1.12A equals A times B. Again, we're looking for A, so, oh yeah, so I wrote it out over here. So R in, so if R out is, I'll write it out here, R out is A, then the R in is going to be B. And so they gave us the value of the inner radius, which is 0.009. Wait, let me make sure that's right. Centimeters. Okay. No, that should be 0.09. Yeah, so that's going to be B. Rn is B. And so we can plug in values. So we get 1.12 times 0.09. We get essentially 0.1. 0.1 minus 1.12A equals A times 0.09. Let's see. Okay, and so from here we just move that or add that 1.12 times A to this one, and then we get 0.1 equals 1.21A, and then A from here will equal, so you divide 0.1 by 1.21, 0.1 divided by 1.21, and then we get, this is in meters, I can move over twice, 8.26, or leave it as is for meters. I'll just put it back to centimeters since they gave us the inner, actually I converted, I might as well just keep it in meters at this point. So 0.0826 meters, and that is for part F. Okay, so a lot of algebra. So now to part G. It says if the potential of the inner shell is 355 volts, 355 higher than the potential of the outer shell, what is the capacitor charge? So we're looking for Q. So let's see here. Okay, yeah, we can just use the same equation we had used for question 2. So Q equals CV, looking for Q. And we have, yeah, they gave us potential, and we already have capacitance. So 125, again, tiny number, times 10 to the negative 12th, because it's pico, times 355, and that should equal our answer. Okay, so we get 4.43, I'll say 4.44. And then that's 10 to the 8th. I'll just say, yeah, I'll just actually just leave it as times 10 to the negative 8. Coulombs. Yeah, because I think it would have had to have been would have had to have been times 10 to the negative 9 to do nano, which is what I was thinking of. Okay, so, and then part H asks for the, well, first it says if the potential of the inner shell, again, is 355 volts, higher than the potential of the outer shell, what is the surface charge density of the outer shell? So surface charge density, equations that we used before involving surface charge. Okay, no, we can't use those. Let's use this one. So we're looking for sigma outer. Okay, so sigma outer equals charge we just solved for over 4 pi, and then it says, let me make sure I get this one right. Okay, so the outer shell. So we said outer shell. Okay, so that's going to be b squared. So looking for this guy, go down. So we have already got Q times 10 to the negative 8th. 4 pi times, or wait, was it? Yes, or 0.09 squared. Okay, let's do that out. That should give us the surface charge density for this equation here. Yeah, okay. Q negative 8, 4 pi, 0.09 squared. 4.36 times 10 to the negative 7th, but that's going to be a negative value because we're talking about the outer shell. So that will give us negative 4.36 times 10 to the negative 7th. And that is going to be in units of coulombs per meter squared. That is, what's that? EFGH. I think part HI is talking about, okay, so yeah, now they want us to do surface charge density of the inner shell, which is just going to be, instead of B, it's going to be A. So in Q 4 pi A squared. So the only thing that's changing is going to be our A is equal to 0.0826. Oh. 0.826 squared. 5.18 times 10 to the negative 7th, but this is going to be positive since we're talking about the inner shell. .18. I want to make sure I did that right. 8.6 squared, 0.826. Yes. -7 per square meter. All right. And then now, okay, ran out of space here, so let's move on to parts J, I believe it's through L. Yeah, J through L. So 24.4.4. 444, a lot of fours. Okay, so part J gives us information. It says a cylindrical capacitor has a capacitance per length of 69 picofarads per meter, and then it's asking for what is the ratio of the inner radius of the outer cylinder to the outer radius of the inner cylinder. So this one took me a second to kind of wrap my head around, but I do remember it. So we're going to want to use this formula here. We're going to use 2 pi times E naught L divided by natural log of RB RA. So we're looking for that ratio, the RB over RA. So we are given, let's see here, we're given the capacitance per length. So we're given C over L. So let's see here. Since we're given that information, we can, I think here, yeah, so we can divide L over and get C over L, and then we can okay, and then we just multiply that by, and then essentially divide that over, and we get 1 over 2 pi E naught, not L, I mean L, but E naught equals, oh, it's still going to be, I almost goofed. It's still going to be 1 over natural log of RB over RA. So let's see here. So yeah, they gave us this bit of information, C over L, because they gave us capacitance per length, or per unit length, which is 69 and picometer. So again, pico is so that's essentially like saying 69 times 10 to the negative 12th. So we have yada 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 equals, let's start doing this here. So essentially that's the same as saying C over L is 69 times 10 to the negative 12th times, is it 1 over, ooh, no, I have to change this to 2 over 4. So that's gonna, instead of being 1 over 2, it's essentially just gonna rewrite to be 2/4. So we get, let's see here. Okay, and we get, yeah, times 2 times 9, 10, 4 pi. Okay. That is, yep, that's okay. I just want a little mental. 10, 9 equals, okay, that's going to equal our inverse natural log RBRA. Okay, so let's do that. 69 times 9 times 10 to the 9th. 1.242. So okay, so we can just essentially swap this numerator and divide this. Then we get 1.242 equals, now we have natural log RBRA, and we can just do, what is that? We do, yeah, so e to the natural log of that, that's going to cancel out, that's going to cancel out. And we do that to the other side, so now we get e to the 1 over 1.242, and then we're left with that ratio. So whatever we get this is going to be our answer for RB over RA. So let's do that. E, where is E at? Oh, second, e to the 1 divided by 1.242, which is 2.24. So that is our ratio. And that is the answer for, which part is that? That's J. Okay, so we have 2 more parts left. So part K says if the outer conductor carries a charge of negative 8.62 nanocoulombs per meter of length, what is the potential difference between the 2 conductors? Okay, so we can use the same equation we used right here. The Q equals capacitance times potential. So let's do that. Q equals CV, and we're looking for V this time. So we just actually let me not move that around first, because I forgot. I think I have to manipulate this if I'm correct. So okay, yeah. So they gave us charge per length, so that's going to be Q over L, so we can use that value they gave us, and that means we have to do the same for capacitance, and then times V, because if we didn't divide per unit length, then we wouldn't be able to use the information given. So this is going to be that negative 8.26. I'm just going to leave it as 8.26 equals, and then this was the same, C over L was 69 times 10 to the negative 12th times V. We divide that over, and then we get, let's see, 8.2. Ooh. Okay, then we get our result for V in this case is going to be V, or like potential, equals 125 volts. That's for part K. And for part L is a multiple choice question. It says which conductor is at higher potential. So the correct answer is going to be A. It says the correct answer for A is, or the answer for A is the inner conductor is at a higher potential than the outer one, and this is because electric potential, or V for volts, is a scalar value, and therefore a negative value equals a lower voltage, and a positive value will equal a higher voltage. So from that we can say that the inner conductor is going to be at a higher potential than the outer one. I don't know why it's not. There we go. But that wraps up exam 24 for chapter 24.